to the club. Okay. Hey guys, so today we will continue our review session. This will be the second part. And in this review session, I would like to talk more about eigenvalues, eigenvectors, and diagonalization of matrices, and also about similar matrices as well. We will see how eigenvalues and eigenvectors play an important role in dealing with similar matrices and diagonalization of matrices. The problems will be a little bit more difficult today. I hadn't planned to do them yesterday, but well, I didn't have much time because I always try to do as much as I can, and it doesn't always work out. So more about eigenvalues, eigenvectors, and diagonalization. Of matrices. Okay. Please feel free to ask questions anytime you want. All right. And before I even go and do some problems, let me remind you some things about eigenvalues and eigenvectors. And in fact, I will want to remind you, so eigenvalues, as you probably know by now, the eigenvalues and eigenvectors can be found using the characteristic polynomial, right? So let's talk about this. Let me remind you that if, okay, let's consider let A be an n by n matrix, right? And we know that an eigenvalue of A, let us, so remember that an eigenvalue let's say lambda of A is a scalar such that this polynomial, basically it's the eigenvalue is the root of this polynomial, PA of lambda, which is the determinant of lambda times the identity minus A equals 0. Sometimes people write the determinant of A minus lambda I is 0. It's just a minus, right? From the properties of the determinant, it's just a minus in front of it, so it doesn't necessarily interfere too much with in finding the eigenvalues. So this is the what we call the characteristic equation of A, and this guy here, this is what we call the characteristic polynomial. Polynomial of A, right? Keep this in mind. So this is the equation, right? And PA of lambda is the characteristic polynomial. And moreover, we can expand this polynomial. Let's keep this in mind. Moreover, we can expand this polynomial. And we have seen yesterday, we have seen last evening how we expanded this polynomial for 2 by 2 matrices, and you've seen that the coefficients of, so when we expand this polynomial for 2 by 2 matrices, it will be a quadratic polynomial, and the coefficients, as you have seen, are the trace and the determinant, but we will write it anyway. So moreover, we can expand the polynomial, the characteristic polynomial, right? So we will have something like this. PA lambda which is, let me write it with red. PA lambda, which is the determinant of lambda times the identity minus A. This guy is nothing else than just lambda to the power n plus some coefficient here, let's say Cn minus 1. As you can see, the coefficient in front of lambda to the power n is 1. It will always be like this. Times lambda to the power n minus 1 plus so on, C1, this coefficient here, C1 times lambda, plus C0, and this C0. So this is how we identify, this is how we can expand the characteristic polynomial. As you can see, it's a polynomial of degree n, right? And moreover, we can identify some coefficients. Always Cn minus 1 will be the trace of A, and C0 will always be the determinant of A. Keep this in mind. And in fact, we can see this for a 2 by 2 case, and I mentioned this earlier. Let's take the n equals 2 case. So what do we have for n equals 2? PA of lambda is nothing else than just the determinant of lambda times the identity. Let me put here an I2 so that we know that it's the 2 by 2 identity minus the matrix A. This guy will be nothing else than just lambda squared plus trace of A times lambda, right? Plus the determinant of A, right? Well, in fact, here I will be, let me be more specific here. It will be minus, because the coefficient will be negative trace of A. Here is a negative trace of A, sorry about that. Okay, so we'll have this. And of course, we have said that the Cayley-Hamilton says that PA of A, if we take lambda to be the matrix A, this will give us the the null matrix, which will be equivalent with saying that if we replace it here, right, if we plug it in here, you'll have A squared minus trace of A times A plus the determinant of A times the identity, will be 0. Okay, that's the Cayley-Hamilton for 2 by 2. And we have said that we can identify the eigenvalues and the eigenvectors for 2 by 2 matrices. We know who they are. And in fact, we will prove this for, in general, for an n by n matrix. We will show that the eigenvalues, the sum of the eigenvalues will be the trace, and the product of the eigenvalues will be the determinant. All right. Now, I want to do an example of, well, there are plenty of examples that in my notes and also in the lecture notes, how to find the eigenvalues, the eigenvectors of a 2 by 2, 3 by 3, and so on. Also, I posted a video about the diagonalization of matrices, and also you can find them in the notes, etc. Now, let me show you something, how powerful this tool of the characteristic polynomial and basically finding the eigenvalues, how powerful this tool is. So for example, let me do the following problem. I don't remember what number is this. Let me see. Number 7. Problem 7. Let's find the inverse of the matrix A equals 5, 4, 0. So I'm going to take a 3 by 3 matrix. 5, 4, 0, 1, 2, 0, 1, 2, 2. And of course, we want to use the characteristic polynomial. There are plenty of ways to find this inverse, at least 2 or 3 ways. Right? We have seen this. You actually had a problem at the midterm exam to find the inverse of a matrix. But now we want to use the characteristic polynomial. And the characteristic polynomial of A and the eigenvalues of A. Surprisingly, we can actually do this. So we want to find the inverse. Before we even talk about the inverse, what do we need to make sure of? We need to be sure of what? That the inverse actually exists, right? So the matrix is invertible. The matrix A is invertible. And I'll leave this to you as an exercise to show it. Just to compute the determinant. The determinant is not 0, right? And now you have 2 options. You have plenty of options, just like I said, to compute the inverse of a matrix. You can go now compute the cofactors of A, and then you compute the adjugate. Well, you can do this. But now let's use the characteristic polynomial, because why? Sometimes this will play in your advantage. For example, I can give you the following problem at the exam. This could be like something, a multitasking problem. I will say like, let A be the following matrix. Find the determinant, find the characteristic polynomial, find the eigenvalues, find the eigenvectors. Is the matrix diagonalizable? If so, write its diagonal form. Then find the inverse. And then instead of you going, oh, okay, he also asks me to find the inverse. Wow. So maybe I should, well, you have to go back to the adjugate. You have everything there. Since you computed the eigenvalues, the eigenvector, and so on, and then you apply the Cayley-Hamilton equation, then, okay, then there is just one step for me. One extra step for me to do. I don't need to go back and compute all those cofactors and so on, right? All right, so let's see here how we're going to do this. So the matrix is invertible. So I'll leave this to you as an exercise. And now I want to use the characteristic polynomial. So the characteristic polynomial, and PA of lambda is nothing else than just the determinant of lambda times the identity minus A, right? Lambda, I will put here I3 so that you know it's a 3 by 3, although it's kind of obvious, I already mentioned it. And this will be equal to, okay, let's write it. And this will be the determinant of, let me write it like this. Okay, the determinant of the following. This is lambda 0, 0, 0, lambda 0, 0, 0, lambda, minus the matrix A, right? So let's write it like this. 5, 4, 0, 1, 2, 0, and 1, 2, 2. And this would be equal to And now we're going to do the computations. It will be the determinant of this matrix. Let's write it. Lambda minus 5, 4, 0. Negative 1, lambda minus 2, 0. Then you'll have negative 1, negative 2, and lambda minus 2. Okay, and I will leave it to you to show that this is in fact nothing else, so that I don't need to do all these computations here in computing the determinant, so that we don't have to lose more time with something that you can do by yourself. This will be something like this. Lambda minus, it will be a degree 3 polynomial. It will be, according to my computations, let me see, just a second. This will be lambda cubed minus 9 lambda squared plus 20 lambda minus 12. Okay. And this can be easily factored into, well, lambda minus 1, lambda minus 2, lambda minus 3. Okay. And now, the funny thing is that I know the eigenvalues. The eigenvalues are lambda 1 equals 1, lambda 2 equals 2, lambda 3 equals 3. These are the eigenvalues. But anyway, I'm not asked to find the eigenvalues. I'm asked to find the inverse of this matrix. All right, so I know the characteristic polynomial. Let's keep this in mind. The characteristic polynomial. So PA of lambda will be, is this guy right here, lambda cubed minus 9 lambda squared. So let's write it again. Plus 20 lambda minus 12. Okay, what does Cayley-Hamilton says? Let's go back. It says the following. Well, I said it here for 2 by 2, but it actually, Cayley-Hamilton says it holds true for n by n. Let's write it here. PA of A will always be the 0 matrix. That's Cayley-Hamilton. Keep that in mind, always. In other words, the matrix A will always be the root of its characteristic polynomial, always. In the case of 2 by 2 matrices, of course, I'll have this, and it will translate into A squared minus trace of A times A plus the determinant of A times the identity equals 0. And we can go on for n equals 3 and so on. So keep this in mind. Now let's apply this to our situation here. So we have that PA of lambda is this, right? By Cayley-Hamilton, it follows that PA of A equals 0, 3, right? Or this will be equivalent with what? Let's look at who P of A of lambda is. So we'll just replace lambda by A. So it will give us that A cubed minus lambda A squared plus 20A minus 12 times the identity. Pay attention here. E of I3, sorry, not I2, is 03. That's what we get. And from here, we have to deduce, we have to find who A inverse is. We know that the inverse exists. So what can we do here? We need to play around with this equality here. So what should we do? Let's write it in the, we need to find, let's keep in mind what we need to find, A inverse. I think this could be like a very nice exam problem, something like this one, to find basically everything for a matrix. Yeah, why not? Okay. So what would you suggest here to do? We have done a similar problem in one of the review sessions. It was for 2 by 2, a 2 by 2 matrix, but we have done a very similar idea. Look at this equality. Let's rewrite it. We have that a cubed minus 9a squared plus 20a equals 12 times the identity, right? And now here I have a common factor, which is equivalent with basically I'm just doing operations with matrices. There is nothing else I do here, just that. This is equivalent with a times a squared minus 9a plus 20 times the identity here equals 12 times the identity. Right? Now what to do? I can, since the inverse exists, I can multiply to the left by A inverse here, right? So multiply to the left by A inverse, and we have, what do we have? We have A inverse times A squared minus 9a plus 20 equals equals what? It's 12 times A inverse, right? So now this guy here will be the identity. And now we will have that, this gives us that 12 times, in fact, A inverse is nothing else than just 112 times A squared minus 9a plus 20 times the identity. And that's it. This is how we find the inverse. I think you get the idea of how to find the inverse of a matrix using the characteristic polynomial. Right? Is it clear for everybody? Well, the only secret here was just this guy, this thing here, the Cayley-Hamilton. That's it. I think this you can find, there are plenty of other examples that you can find. And if you want, you can take the problems from from previous exams, yeah, from the midterm exam, and then you can just apply this method to see if you get the same results. Okay. Now let me do another problem. I want to do as many problems as possible, and in fact, you know, I want to prove that. Okay, that's the problem. This was problem 8. I don't want to. I just want to go and prove that the sum of the eigenvalues is the trace, and the product of the eigenvalues is the determinant. Let A be an n by n matrix, because we will use this, and we actually use this in problem 6. Let A be an n by n matrix, and let lambda 1, lambda 2, lambda n be its eigenvalues. Show that we have the following. The trace of A, right, which is defined as, you know, as the sum of the element of the entries on the main diagonal, is nothing else than just lambda 1 plus lambda 2 plus lambda n. And the determinant of A is nothing else than just the product of the eigenvalues, lambda 1 times lambda 2 times lambda n. So we want to prove this. And now what we're going to do is the following. We'll use, well, you can prove it in a traditional way, like using the characteristic polynomial, but I have to tell you more about the Viet's relationship. How do we express the roots in terms of the coefficients? And I don't want to go into that. I have to require some background from algebra, and I don't. Well, that is more a direct traditional way, but since I have this tool of diagonalization, why not use it? Okay, and we want to use this, why not? In fact, the proof is a beauty. All right, there was this theorem that I gave you in the notes, and I think you can find this in the last lecture, lecture 17. And I'll suggest you have a good lecture 17. Yes, I think so. It was the last lecture about the diagonalization, which says basically the following. If I have an n by n matrix and that has n distinct eigenvalues, then I can diagonalize the matrix. In other words, since A is an n by n matrix, and lambda 1, lambda 2, lambda n are its eigenvalues, it implies that A is diagonalizable, and moreover, there exists an invertible matrix P such that P inverse times AP is nothing else than just this matrix D, let's say. And this matrix D will be a diagonal matrix. And guess what? On the main diagonal, you'll have the eigenvalues of the matrix. Lambda 1, lambda 2, lambda n, and you'll have 0 in rest. Wait. No, upper triangular. Anyway, okay, let me, not diagonal. You'll have here 0, and here you have some elements, non-zero elements. But anyway, it doesn't really matter. What matters is that you can write it like this. In fact, diagonalizable. Maybe I should be, that's a little bit, okay, let me put it like this. So it can be triangularized because it's not quite diagonal, right? It's almost diagonal. But anyway, it doesn't matter. The point of the matter is that you'll have the eigenvalues on its main diagonal. And now it's quite clear. If you look at the product, this is a triangular matrix. What did we say about the triangular matrix? If we take the determinant of this, if we apply the determinant of P inverse times AP is what? Is the determinant of the triangular matrix. And what do we know about the determinant of triangular matrix? We said that is the product of the elements on its main diagonal. So it will be lambda 1 times lambda 2 times lambda n. Great. But on the other hand, this guy here, by applying the usual properties of the determinant, we know that the determinant is multiplicative, and also it commutes. Determinant of AB is determinant of BA. So we can play around with this the way we want. It will be the determinant of, let's put P here, it will be P inverse AP times A. Or you can write it as the determinant of P inverse times the determinant of A. But this guy here is nothing else than just the identity. So this will be the determinant of the identity times the determinant of A. Well, the determinant of the identity, we know that this guy is 1. So this is nothing else than just the determinant of A. Right? Great. So we now look here, we have the determinant of A. Also, we know that this is this. So it follows that the determinant of A is the product of the eigenvalues. Okay, now let's see for the trace. For the trace is the same thing. Let's look again at this matrix. That's the only thing you need to look at, this right here. In fact, ouch. So you need to look at this matrix here. And now, since we apply the determinant, now we apply the trace. Let's apply the trace. And we have that the trace, let's look here, the trace of P inverse times AP is nothing else than the trace of the triangular matrix. But the trace of the triangular matrix, let's look on the main diagonal on the trace. The trace is always defined as the sum of the entries on the main diagonal. As you can see on the main diagonal, I have the eigenvalues. So it will be lambda 1 plus lambda 2 plus lambda n. And now, by the properties of trace, this will always be equal. You know that trace commutes also. So we'll have that trace of, this is trace of trace of AB is trace of BA. So let's consider this like a A and this is a B. So it will be trace of P inverse times A. But this guy is the identity. So this will be equal with trace of A. The identity times A, which is trace of A. Again, if we look here, this guy, it will be equal to this guy. And again, the same story. The trace of A is the sum of the eigenvalues. And that's it. What do you think? Was this hard? It's a bit tricky though, because you have to know. Well, here, I think the theorem that I mentioned in with the diagonalization was because here I said the matrix is, well, I didn't say diagonalizable, but it's more like an upper triangular matrix. And the theorem that I gave you in class was, I think it was, I don't know, in my notes, was something like this. If an n by n matrix A has n distinct eigenvalues, pay attention, then the corresponding eigenvectors are linearly independent and A is diagonalizable, right? That's what we said. We said, so this is what happens in this case. You can write it in, well, I didn't say about the eigenvalues being distinct, right? I didn't say that. I just said it has eigenvalues. Some of them can repeat themselves. But in any case, you can always find an invertible matrix such that P inverse times AP will always look like this, an upper triangular matrix, right? Okay, that's the only thing here, but the rest is quite clear. Is it clear for everybody, this problem? Okay, now let's see another problem where we want to use these kind of things. Problem 9. Let me think. In fact, there is this problem that I liked a lot, and yeah, determine. Let's take a 2 by 2. Let's not complicate ourselves too much for the moment. Determine whether the matrix A, which is, let's take a 2 by 2, 1, 4, 2, 3, let's say. Wait, let me see. Okay. Determine whether this matrix is diagonalizable. If so, find a non-singular matrix let's say S. Okay, let's keep the notation P such that P inverse times AP equals a matrix D, where D is diagonal. Okay. Okay, I want you to think of this problem a bit. So look at it. It's a pretty standard problem. Also, I gave you, if you look at the video and also the notes, I gave you an example of a matrix, a 2 by 2 matrix that was not diagonalizable. So I hope, yeah, this one is good. So the first step that you need to do is just to find, write the characteristic polynomial, find the eigenvalues, their corresponding eigenvectors, and then we'll see, we'll play around with that. So let's see, what are the eigenvalues? Did you compute them? So first of all, we need to write the characteristic polynomial. Of A. You got -1 and 5. Yeah, I think that's correct then. Yep. Let's write it anyway. So the characteristic polynomial of A is PA of lambda is the determinant of lambda times the identity minus A, which will be, okay, let's write it, which will be nothing else than the determinant of lambda minus A. Oops. 1, 4, 2, 3. Okay, so this will be the determinant of lambda minus 1, -4, -2, and lambda minus 3. Okay, clearly the determinant of this is lambda minus 1 lambda times lambda minus 3 minus 8, right? Okay. And this will be equal to what? To lambda minus 1, right, times lambda minus 5, correct? In fact, let me just write it so that we can see it clearly. This will be lambda will be equal to lambda squared minus 4 lambda plus 3 minus 5, right? And this can be factored into lambda plus 1 times lambda minus 5. And yes, just like Kobe said, yep, we have, this implies that lambda equals, so the eigenvalues are lambda 1 equals -1 and lambda 2 equals 5. These are the eigenvalues. And now what well, I'm going to ask you, is the matrix A diagonalizable? Before we even start writing the eigenvectors, because we need them. That's my first question to you. Is my matrix A diagonalizable or not? What do you think? Is it? What did we say earlier? And also we said that what? If an n by n matrix has n distinct eigenvalues, right? We said that A is diagonalizable, right? We said this. Right? We even said more. We said that if an n by n matrix A has n distinct eigenvalues, then the corresponding eigenvectors are linearly independent, and moreover, the matrix is diagonalizable. Keep that in mind. Let's write it, because I want to make sure that you get this. Remember that if an n by n matrix has n distinct eigenvalues, right? Then the corresponding eigenvectors right, are linearly independent and A is diagonalizable. Keep this in mind, please. This is important. So in our case, how many do we have distinct eigenvalues? Yes, they are. They're distinct eigenvalues. Great. Then we can infer that clearly this implies that that A is diagonalizable. Ouch. Okay, so we know that our matrix A is diagonalizable, but we only found the eigenvalues. We need the eigenvectors. We need the corresponding eigenvectors. This is important. And we need to find those corresponding eigenvectors. Right? For each eigenvalue. So let's do this. So let's see, oh my. Let's see, for lambda 1 equals -1, right? Yes, -1. I think this is what you, yeah, -1 and 5. Okay. Let's see, for lambda 1 equals -1, what do we have? We have that -1 times the identity minus a, this guy, will give us what? Will give us this -1, 0, 0, -1, minus a, which is, wait, what is a? 1, 4, 2, 3. And this will be the matrix -2, -4, -2, and -4. Okay, that's great. So in other words, this will be nothing else than just the negative time 2, 4, 2, 4. Wow, look at this matrix. Well, clearly, if you do basically to find the eigenvector, why you need to multiply this by this vector x1, x2. Here, let's write it, x1, x2, and you set it equal to the 0 vector. So that's the system, right? And you find, but instead of doing this, you just need to perform elementary. So, and we need to find x1 and x2. Okay. In other words, as you are used by now with solving systems of linear equations, in this case, this homogeneous system, we are interested in performing elementary operations to this matrix. So elementary row operations to this matrix. So that we can come up with the row reduced, so that we can obtain an equivalent matrix in row reduced, in row echelon form, if you want. Okay, so let's do this. Let's look at this matrix. 2, 4, 2, 4. Oh my, this is very nice. What operation should we do here? Keep in mind that we need to come up, this guy should be 1 here, transform into 1, and it doesn't matter the order. Of course, you can divide by 1/2 if you want, but let's, so this is R1 and R2, and this will be equivalent with the following 2, 4, and now I'm gonna, so this is R1 here, and this will be R2 will be my R1 minus R1 minus R2 minus R1 will be my new R2. So this will be 0, 0, right? And now clearly you can get rid of these two by multiplying two. So this will be by multiplying by 1/2. So this will be 1 and 2, 0, 0, and this is R2. And my new R1 will be 1/2 R1 is R1. Okay. And now it's in row reduced echelon, row echelon form. And it follows that the eigenvector will be the following. The eigenvector of lambda 1 equals -1 is of the form let's say t times, and we'll have this vector -2 and 1, the t real. Okay? In other words, it will be for a non-zero scalar t. Let's keep this in mind. Similarly, let's see the other eigenvalues, lambda 2 equals 5. Let's see. In this case, we have the same thing, 5 times the identity minus a. This will be 5, 0, 0, 5 minus, what was the matrix A? I always forget. 1, 4, 2, 3. Okay. 1, 4, 2, 3. And this will be equal to 4, -4, -2, and 2. Yeah, it doesn't matter. Okay. Now, again, this will be -4, 4, 2, -2. Anyway, it doesn't really matter that much. So you can perform again elementary operations, and I'll leave it to you as an exercise. So performing elementary operations. We get what do we get? Let me see. I think I've done the computations here. So we get that this matrix here, -4, 4, 2, -2, this will be, so we'll leave it to you as an exercise. Its row echelon form will be something like, wait, what is that? Just a second. Where is it? Okay, so it will be 1, -1, 0, 0. Okay. Okay, at some point you'll get this. Anyway. Yeah. All right. So the eigenvectors here will be something like this. Let's say will be something like, let's use another S times, S times 1, 1. So this will be the corresponding eigenvector. Of course, for some S real number. Now, we know that since this is a combination, we only care about these vectors here because it's spanned by this one and by this one. And now we form the matrix P. So we define P as the matrix whose columns will be the eigenvectors. In other words, this will be, the first one was -2, 1, and the second one was 1, 1. That's the matrix P. Of course, this will be invertible. You can find the inverse. P is invertible. You can actually find the inverse. And by the diagonalization procedure, guess what? If you compute, if we compute P inverse times AP, this will be nothing else than just at some point, and I'll leave it to you as an exercise here. I don't want to do the computations, but I'm sure you can do them by yourself. It will be this diagonal matrix D, which is given by, I'm just going to copy it, -1, 0, and 0, 5. And guess what? What do you see on the main diagonal? Oh, not this one. What do you see on the main diagonal of this matrix? Just look at it. Look. You see nothing else than just the eigenvalues. The eigenvalues of A. And voila, that's the problem. You see, it's pretty straightforward. Also, I would suggest you look at the videos. I've done this. Again, it's very straightforward. Now let me do another problem, a little bit more tricky than this. So this was problem number 9, problem number 10. Now let's see, what do I have here? There's so plenty I want to do. Okay, let me do this tricky one. I wanted to put this on an exam, but maybe not. Okay. The problem says the following. Suppose that the matrix A is diagonalizable. Keep this in mind. This is a pretty huge information at this point. It's diagonalizable. It's diagonalizable n by n matrix. Okay, and has only 1 and -1 as eigenvalues. And again, another important information. You see, I have an n by n matrix. It has only 2 eigenvalues. Definitely, they're not distinct. And well, show that. Guess what? This matrix, if we square it, is nothing else than just the identity. Where IN is the n by n identity matrix. This was a very nice problem. I think it was given at, if I look here, it was a Stanford linear algebra exam. Okay, look at it a bit, analyze it a bit. Like I said, this is it's not a hard problem, I would say. It's a bit tricky. So look at it. You have, I already underlined the essential information. Think about it for, let's say, a couple of minutes. I have plenty of other examples, but anyway, I wanted to do this one because it's a very nice problem. So this is a proof type question. You have to prove things here. Think about it for a couple more minutes. What do you think? Well, let's see. Let's analyze each term. So I have a matrix A, which is diagonalizable. It's an n by n matrix. So what can we say about that? Since A is diagonalizable, what do we know? This means that it follows that there exists an invertible matrix P such that what? Such that P inverse times AP is this matrix D, which is a diagonal matrix. And moreover, D, and let's write it, we'll have here the eigenvalues, lambda 1, lambda 2, lambda n. You will have 0, 0. In fact, wait. Anyway, it doesn't really matter. Diagonal, upper triangular, it doesn't really matter. Right? But what matters is that we have these eigenvalues here. But now these eigenvalues are all of them are negative 1, 1. Lambda i's, which belong to this set, plus minus 1. Okay, so we have this. So the diagonal entries of this matrix are negative 1, 1. Ouch. Oh my goodness. The diagonal entries are these are the diagonal entries Are all of them negative 1, 1? Right? The diagonal entries of D. Well, what does this mean? Well, let's see. The question is, from this relationship right here, can we write A? Well, we can. Let's look at it. From P inverse equals A times AP equals D, we can multiply. We multiply by P to the left. And we have what? And we have that P inverse times AP is PD. But this guy is the identity. Or equivalently, we have AP equals PD. Now we multiply by what? By P inverse to the right. And we have, what do we have? We have AP P inverse equals PD P inverse. Again, this will be the identity, or we will have that A is PD P inverse. So wow, we can actually write A. So from this relationship here, from this guy here, we went all the way to this guy right here. Okay, great. Now it's clear what to do. A squared is nothing else than just A times A, which is PD P inverse times PD P inverse. We multiply by itself. Well, we know that this is associative, so we can write as PD P inverse P, right? D P inverse. As you can see, this guy here will annihilate, so this will be just the identity. So this will be equal to what? To P D P inverse, which is PD squared inverse. But this guy, but D squared is nothing else than just the identity. This will be the identity. And there you go. So A squared is the identity. Is okay, let me write it. It's P inverse times the identity, which is the identity, and that's it. Right? Keep in mind that the diagonal entries are only negative 1, 1. When you square them, it will be just, in fact, it will be diagonal here. Now I said upward. Okay, let me be more specific. 0, right? So when you square them, it will be just the identity, and that's the problem. Anyway, it's a little bit more involved. Like I said, I was planning to put this as a problem, as the last problem for, but anyway, I had another one in mind. Okay, guys, I think I'm going to stop here. Thank you very much. Stop the